Now let's discuss in more details about harmonic motion. You hear harmony a lot in the music industry, and you hear it about any group or of creatures or of humans working together, or an automated factory. You say this factory is working in harmony, and we can say this music is full of harmony. Harmony means things are being synchronized to each other, but in physics it is similar but a little different. Before we go there, let's talk about Hooke's law. We talked a little bit before about it. Hooke's law is mainly focused on the springs and the forces being applied to the springs, and the relation between the force applied to the spring and the displacement of that spring. What did Hooke do? He determined that the deformation is proportional to the applied force, and this can be said as force varies directly with the displacement, and can be written as F is proportional to the displacement of the spring X. The relation is known as Hooke's law. The definition of Hooke's law: the deformation of an object is proportional to the force causing that deformation. Long story short, you have a spring being naturally resting over here. You have a force applied on it. Depending on the amount of force, this spring will be squeezed from the initial top point of the spring to the new point. You have a 5 centimeters difference. That's what we call X. And we have here a 20 grams box that can be translated into force. You can see the 20 gram box is squeezing the spring even more, so the X is 10 centimeters. And a higher force or a higher weight, of course, force and weight are, F equals mg. F equals mass by gravity. So if you have the mass multiplied by gravity, you get the force. So we're talking about force in one way or another. So you have here as having x0 over here, or x naught, x initial, and the x final is here. So the total x is 15 centimeter deformation for that spring. So each spring is different. The force required to deform it will change from spring to spring. The stiffness of the spring, or the spring constant, is different between each spring depending on the material made out of, and the angle and the amount of force applied to it. And we annotate the spring constant as K, and you can say Hooke's law is represented mathematically or physically as the force equals the constant of the spring K by the spring displacement X. So the F is the applied force that extend or compress the spring, because the force could be pushing or squeezing the spring or pulling it away. And the K is the spring constant. X is displacement from the equilibrium position. Now, if we want to draw Hooke's law as we did previously, we will redo it here in more details because it is related a little bit to harmonics. So you have a spring and you have Newton's scale over here. You pull the scale with the hook of the spring. You apply a force Fa, and this is the initial point or the resting point for the spring. That's x naught or x initial. Then you pull it away with a force Fa. The displacement was changing. If you draw a table, for each moment the displacement is changing and the force is changing. Let's say at 0 displacement you had a force of 0. At a force of 5 Newton you had 0.1 displacement. At a force of 10 you had 0.2. At a force of 15 you had 0.3. At a force of 20 you had 0.4. So you draw the displacement with force, and you find a linear line for force versus displacement of the spring. This linear line, we can calculate the slope for it. That will be the change in force over the change in position of the spring or the displacement. That would be final force minus initial, 20 minus 0 over 0.4 minus 0 would give you 15 newtons per meter in this case. Let's take an example. Determine the spring constant in which the student attaches a force meter to one end of that spring and the other end to the wall. Plot the values on the graph of force as a function of displacement using line of best fit. Determine the spring constant. We have to find the spring constant. That's our table, force versus displacement. We can take point by point we can say force is y and displacement is x. So you can say x and y. So at point 0, 0, we draw a point. At point 1 and 0.25, we draw a point, and so on, and we draw a linear line. Let's find the slope. Slope in this case would represent the spring constant K, would equal delta F over delta X. If you rearrange the equation, K would equal 0.6 minus 0.2 over 0.3 minus 0.1 would be 2 newtons per meter. There is something called the restoring force. If you have a spring, you can push it and squeeze it, and you can pull it and extend it as well. When you pull it, that is called the restoring force. In this case, we have Fa pulling the spring away. We have Newton's scale that's telling you how much force are you using or pulling the spring with. And you have the F return. And you have the initial displacement starting here. The new displacement is right here to the right hand side. You draw your convention, which way is right, which way is positive, and which way is negative. Positive is to the right in this case. As you pull Fa, there is a force called F return. That's what you can call it as the tension of the spring, trying to bring it back to its natural position and be able to maintain equilibrium. So the restoring force can be represented in terms of Hooke's law as F, restoring force, or Fr, equals minus K by X. Why minus? Because always the return force is pulling against the applied force, because it needs to bring back the spring to its natural position. Let's take an example. You have a spring with a constant K of 30 newtons per meter. Spring is pulled to distance 1.5 meter from equilibrium. What is the restoring force? Restoring force equals minus K by X. We have K and we have X. Let's replace them in the equation. That would give you minus 45 newtons, which means the restoring force is 45 newtons to the left, assuming the right is the positive direction.